Hi. In the previous 3 lectures, we talked about tipping points. And we saw 2 models, right? We saw a percolation model and we saw a diffusion model. And both of those created tips. What I wanted in this lecture is give some formal definitions of tipping points. And I'm going to make 2 distinctions. I'm going to distinguish between what I call direct tipping points, where when I change that variable, it causes that variable to tip, versus contextual tipping points, where the change in some action or the change in some parameter causes the system to change to result in the tip. So in the percolation model, in the forest fire model, we had a change in the density of trees or in the density of the soil, and that caused the system to tip. So that's a contextual tip. I'm also going to talk about tips between and within class, right? Remember we talked about sort of equilibrium systems and complex systems and periodic systems. Systems can tip from one of those states to another. Now to understand all this, I've got to start with something else. I'm going to start with just some very basic graphs describing some dynamical systems so we can better understand how these different tipping points operate. So we're not going to do the mathematics of dynamical systems. We're just going to draw some simple graphs, and they'll help make sense of a lot of this. So here's the basic idea of a dynamical system. What you've got on this axis is, here's this variable x, and what this is telling you, this little x dot, is telling you how x is going to change. That's what this line tells us. So if the line is positive, if it's positive, it means that x is going to move in this direction, and if the value is negative, like it is over here, it means x is going to move in this direction. So if you look at this particular graph of a dynamical system, it shows a stable equilibrium. If I start here, I'm going to move in this direction to y, right there, to this point y over 2. And if I start here, I'm going to move in this direction and go here. So if you perturb the system in any way, we're going to go right back to that point. So it's stable. Here's a more complicated dynamical system. In this dynamical system, if I'm in this region, the value of the function is negative, right? So I'm going to move in this direction. If I'm in this region, the value of the function is positive, so I'll move in that direction. And in this region, the value of the function is negative, so I'm going to move in that direction. So what that means is if I start here, I'll go to this equilibrium, right? And if I start here, I'll go here. And if I start here, I'll go there. So what you get is you get a stable equilibrium here and a stable equilibrium here. Now notice this point right here where the value is 0 is an equilibrium, but it's a tipping point because it's unstable. Any slight change in the variable, if I just move it a tiny bit to the right, I'm going to head over to this equilibrium. And if I put it a tiny bit to the left, I'll head over to 0. So you go from a stable equilibrium to an unstable equilibrium to a stable equilibrium. And this unstable equilibrium we can think of as a tipping point because any slight movement, any change in that variable will lead to a large change in the variable. That's what I'm going to call a direct tip. So you're sitting at some unstable point right here, and if I just moved it in either direction, right, I'm going to roll down the hill and either go to this equilibrium or that equilibrium. So that's a direct tip. Tiny change in the variable itself leads to a big change eventually, right, in the value of that variable. So formal definition, direct tip, small action or event has a large effect on that end state, right? So you change the variable a little bit, and it has a huge effect on what happens in the long run. So for example, World War II, right? The killing of Archduke Ferdinand, right? You could argue that this resulted in this tip where the whole world goes to war and tens of millions of people die, right? But this sort of just tipped the whole system, right? And led to, alliances forming and, nations waging war against one another, all because of this one act, right? It was a direct tip. Now, in the Vietnam War, right, one of the things that escalated the war was the bombing by the North Vietnamese of Pleiku. Now, McGeorge Bundy, who was the National Security Advisor at the time, he famously said, Pleikus are like streetcars. What he meant by that is that streetcars come down the road all the time. That Pleikus, these events that can escalate war, they happen all the time. So what he was saying basically is that even though Pleiku was what I'm going to call a direct tip, right? That, yes, true, it was a tipping point in the war, but they come along all the time because what he was saying is the context, right, the environment was such that it was bound to happen. So if we think back to our percolation model, what McGeorge Bundy was saying is, look, it was going to percolate. The system was going to tip. The probability was above 59.27%. So all we needed was one drop of water and it was going to race its way through. Or all we needed was one match and the whole forest was going to catch on fire. And that those matches, Pleikus, are like streetcars. So the point here, and it's an interesting one, is even though we often focus on the direct tip, we focus on the killing of the Archduke, we focus on Pleiku, What's really going on in a lot of these cases is that what's causing those direct tips is a change in the context, right? So let me explain how that can work. So here's our function, right? And we've got, this system where here's a stable equilibrium, here's an unstable equilibrium, here's a stable equilibrium. Well, what happens if the context changes and moves this line down a little bit, right? Well, if it moves this line down a little bit, then all the arrows point in this direction. So this equilibrium that was stable, right, is no longer stable. So what we've got is we've got a contextual tip. A change in the environment, just by a tiny bit, has an effect such that it wipes out, right? In this case, by the environment causing this curve to shift down, it wipes out this equilibrium. The dynamical system always points to the left, and what you get is you get a completely new equilibrium at zero, right? So a contextual tip is a change in the environment. So in the percolation model, it's sort of filling in more squares. In the forest fire model, it's growing more trees. In a social network model, it's making more connections. And it's, in doing that, it makes the possibility of a direct tip go way up, and it means that the end state of the system is likely to change. So remember, we saw that in a percolation model. This is a change in context, right? It's a change in sort of the number of squares filled in. Remember also our SIS model, right? R0 was the basic reproduction number. When we change the virulence of the disease, or we change the rate at which people contact, or we change the rate at which people sort of recover from the disease, that's changing the context in which that disease spreads, and it's changing the likelihood then, if, once the disease gets kick-started, that it's going to spread throughout the population. So changing the context is what makes these direct tips possible. Okay, so we've talked about direct tips, where the variable moves a little bit and causes itself to move even further, right? Sort of bootstraps itself. And then contextual tips, where the environment changes. I want to make one more simple distinction. Remember, we talked about 4 different types of systems, right? Equilibrium systems, periodic systems, random systems, and complex systems. A system can tip with